that are attached to sulfur is going to have to make another bond with the next fluorine, right?
Yeah.
So here's what happened. This one's an exceptional.
Doesn't work.
It goes out in 3
Oh, it works.
dimensions. It goes out in 3 dimensions.
Yeah, but even when you had CH4, that's 3-dimensional too. Or do you need a 4th dimension, Dawn?
It goes through time.
Right, yes. No.
That's crazy.
What happens is sulfur now is big enough of an atom that it can have more than 8 electrons around it. And so it's going to go ahead and attach to all 6 fluorines. It looks like this. There's 1, 2, 3, 4, 5, 6.
What's the maximum?
The maximum for sulfur would be 6. Iodine can make 7 bonds. And I think that's it. I have never seen one with more than 7. And now, here's the story on this one.
Was it super unstable?
Is it what?
Unstable.
No, SF6 is a little bit unstable, yeah, because the S is a positive 6 oxidation number. But it exists, and it's a compound.
And it works.
I've never used it before, and I can't tell you anything about it. I think it's a liquid, but I don't know much.
So the red ass is zoomed also out.
Yeah.
Because they'll know
Yeah,
exactly
yeah.
what we
When we Skype with them.
I never want to say like talk about it.
Okay, so let's see. 3rd row and larger. Sulfur is in the 3rd row of the periodic table. Those elements and larger, they can expand their valence shell to have more than 8 electrons. So sulfur qualifies. It's in the 3rd row of the periodic table. It can get more than 8 on it, and it does. Not always. Sometimes it's good with 8, but it can have more than 8 too. Andrew? Yes, but you don't need to know that. Like sulfur is not going to have more than 12. It's going to have 12 in this thing, and that's it. I can go ahead. What happens is this. The reason I say 3rd row is because now we're up to the 3rd energy level of electrons. You know that the 3rd energy level has 3s, 3p, and 3d. Now, the sulfur's not even to the 3d row yet. That's in the 4th row. Sulfur's only in the 3rd. However, the sulfur is going to use 3s electrons, or 3s orbitals, 3p orbitals, and some of its 3d orbitals and hybridize all of them. That's what happens when sulfur can expand. And phosphorus can do the same thing. There is probably you'll run into this chapter, a compound that's PCl5. The phosphorus is going to wind up with 5 chlorines on it, that gives it 10 electrons. And that's fine. So this is completely fine and legal to put 6 fluorines on the sulfur. And I'm just not quite finished. And this is annoying, but I am looking for this. When I ask you to do a dot structure, I do expect you to have all your lone pairs on the peripheral atoms like that. So if there should be 48 electrons, I see 48 electrons on it. And there are. You care to count them?
It's just multiplying.
Yeah, I did it.
Yeah. 8
Because
around each, times 6, good to go. Now if the fluorine, or if the SF6 was an oddball, the next one is an oddball deluxe. Check this one out. Xenon difluoride.
It needs to not.
Something seem funny about that?
It needs to not.
It needs to die?
It needs to not.
Oh, to not. All your science life you've been taught that noble gases, oh, they don't make compounds. Well, you know what? They do make compounds. Some of them do. There are several compounds with xenon. Krypton actually will make a fluoride compound that I've seen. Radon can make some. Yeah, the bigger noble gases, they can. For the same reason, they can borrow some of their d orbitals and hybridize them too.
I'm sick of the lies.
Yeah.
After I discovered metal
Also-
alloys, I was done.
All right. Well, now we're going to have to try to make a dot structure out of this. Well, how would we describe this? This is a renegade compound, to put it nicely. Who's going to go in the middle, the Xe or the F? Well, hold on a second. We want the least electronegative element in the middle. I thought the noble gases didn't have values for electronegativity.
But then you added fluorine.
Yeah, if it's going to bond, it's going to have a value for electronegativity. So I lied to you there too.
Plus. Should we trust?
Xe is in the middle.
That doesn't work.
All right, so we're going to put some lone pairs on these. This one is just funny. It makes you shake your head. Oh, we didn't count electrons. I said do the same thing every time, and then I violated.
22.
Xe has 8 valence electrons plus 7 times 2 is 22 electrons. That's what we're looking for in this. How many do I have here?
20.
So this is a case where we have to add electrons. The fluorine atoms are small. They can't have more than 8 electrons around them. So I cannot mess with that or that. So if I need to put on 2 more electrons, it's got to go on the central atom only. So as weird as this is, it's got 8. Just stick another lone pair of electrons.
This is not what I've learned to count.
I know. Yeah.
I feel like you just got lazy.
Yeah, just lazy. Just like, you know what?
Yeah,
Let's
yeah.
put
Well,
two-
I don't know what else to do. I'll just put it there. Yeah, that's kind of what we do. That gives us 22 electrons. That is the dot structure for NCN2. There are exercises in the chapter that are going to ask you to do dot structures and crazy things like this. So here's the bottom line. If you have too many electrons, you need to get rid of some. That's where you make double and triple bonds. But if you don't have enough electrons, then you add them to the central atom. You may wind up adding more than one lone pair to the central atom, and just do it. Okay, one last one that I'm going to ask you to write the dot structure for is the nitrate ion. This one is going to go back to the traditional, everybody gets 8 electrons and nobody's misbehaving. So would you take a moment and do the dot structure for nitrate? How does the structure look? Any distinguishing features?
Do you have to connect it over to the
A double bond. Yeah. And
I did the triangle thing.
you're into the shapes, aren't you?
I mean, that's like,
Hang
because
on.
that was always like important in chem.
Oh, they are.
Yeah,
They are.
yeah,
We're,
like-
we're doing that next.
Yeah.
They are important. I'm hoping that you came up with a double bond structure. The double bond oxygen is going to have 2 lone pairs on it. And the nitrogen will not have a lone pair on it because we had to erase it to make that double bond. The single bonded oxygens each have 3 lone pairs of electrons. And that gets us to the 24. This is an ion. Does it matter which oxygen the double bond goes on? Could the double bond be on the bottom oxygen? Maybe that's where you put yours, or on the oxygen on the right. Or you have it looking different. If we analyze the bonds in nitrate, analyzing means there's an instrument that chemists use to determine what kinds of bonds are in compounds. It's called an infrared spectrometer. They use infrared light, they shine it on the sample, and it goes through a spectrum, the infrared spectrum. And when you get a type of bond that corresponds with a certain wavelength, you get a peak on the infrared spectrum. You would expect the nitrate ion to give a peak for the double bond and then a separate peak for the single bond because they would have different wavelengths.
Wait, why does the double bond work? Oh, never mind. It's 24 electrons.
Yeah, when we had a pair there and a pair there, that was 26 electrons, so we had to get rid of 2 electrons. Sunman, what's the matter?
Oh, never mind. I just,
Anyway, what I was saying was, you would expect there to be, in nitrate to be 2 double bonds and one double bond and 2 single bonds. It turns out though, when you run this thing through the infrared spectrometer, it only gives 1 peak for the bonds, as if the bonds are all the same. How could that be if they're clearly 1 double and 2 single? Those are not the same. And what? I don't know what you're saying, Michelle. Okay, okay. All right. Now, here's what I'm getting at. That double bond could be there. I'm not going to put the lone pairs on. And the double bond could be there. Turns out that there are 3 different ways that the dot structure can look, depending on where we put the double bond.
It's chiral. Is it chiral?
No, chiral is something different.
Okay.
Chiral is when you have a central atom with 4 different things around. But what this is resonance. We talked about resonance way back early in the year. Not that I'm suggesting you need to remember it. You do need to remember it, but you might not yet. When we learned about the benzene ring, we learned that there are alternating double bonds in the benzene ring, and that the double bonds really aren't double. It's really 1.5 bonds all the way around in benzene. Well, the same kind of thing is true with nitrate. Because we could just as likely put the double bond in another place, the overall arrangement of the bonds is the average of the 3. Note that NO3 could be drawn with its double bond in more than one location. This causes resonance. So I'll just go ahead and uncover this. This is what the way we would draw the dot structure of nitrate.
Did we do dot structures in the beginning of like class? Kev? Like you,
In the organic?
yeah, you like made us like draw the dot structures.
Yeah. We're going to do that again next week one day. Oh, no, 2 weeks. We'll do a model activity. It's actually 3 weeks then. Not the week we come back from break, but the week after. We'll get the toys out.
Thursday at half day.
Yes.
What are we doing? Notes? More
Oh,
notes?
it's a full lecture day. Yeah, I got to.